Okay, so we're not quite done with equilibria yet. And so chapter 13, we talked about general equilibrium. In chapter 14, we talked about equilibria of acids and bases. And now we're going to talk about other kinds of equilibrium, most specifically precipitation and solubility, and maybe some others. So if you remember in chapter 4, we learned about solubility rules in which ionic compounds dissolve completely in water. And we had those rules, so mostly the nitrates, the group 1A metals will dissolve, the nitrates, some of the chlorides dissolve, some of them don't. So you can go back and review those. But the main thing is that anything that is completely soluble totally dissolves, but if it's not soluble, it doesn't mean it doesn't dissolve at all. It just means that it dissolves a very little, so it's insoluble or slightly soluble. So we're going to look at the equilibria of these slightly soluble compounds in this chapter. And we're going to kind of look at it from both directions, so we can say how much of that solid will dissolve. Or looking at it from the other way, what will happen if we mix these together? Will we get a precipitate? So this is just a picture showing you. So again, here this is silver chloride. So I'd say that the ions here, these are silver and these are chlorides. So you put the solid into water, and as we've seen, most of it will just sit on the bottom. So most of it will stay solid. However, a few of the ions will separate. And so you might have a few of the ions floating around in solution, but the majority of it stays glom in a glom of solid on the bottom. Now it doesn't mean that but an equilibrium is set up, so the same number of ions will stay in solution. However, it's possible that some of them may precipitate and then others may break off. So they're constantly breaking off and dissolving, but they do. It will stay constant, so equilibrium. So like I said, there's no such thing as insoluble. Even very insoluble compounds will dissolve to a very small extent, so they're sparingly or slightly soluble. And also, like I just said, so there is an equilibrium that's established between the solid and the ions in the saturated solution. So for example, if we look at calcium oxalate, which is does not precipitate, or I'm sorry, does not dissolve very well, we can write the equilibrium expression. So we can write it as its ions, calcium ion and the oxalate ion, just like we did for soluble salts. We'd write it as aqueous. However, instead of a single arrow, we've got our equilibrium arrow showing that we still have a lot of the solid present, but we have some of it in terms of ions. So that's the equilibrium that is established. And then we can write, and just like we did with other equilibrium expressions, we can write the equilibrium expression, and we're going to end up with our constant this time is called the solubility product constant, or the KSP. So it's the equilibrium constant for slightly soluble or nearly insoluble compounds, and it equals the product of the equilibrium concentrations of the ions, and they're raised to their coefficients. So actually, it's probably a little more, let's look at it on the next slide, and it'll make more sense. So if we think back to this equation, so the calcium oxalate dissolving into the calcium ion plus the oxalate ion. So if you remember, if we were going to write the K expression, it would be products over reactants. But if you also remember back a couple chapters ago, when we have a pure solid or a pure liquid, and remember this is a solid, these are aqueous. But a pure solid does never gets included in the equilibrium expression because it's constant. It's basically, it doesn't change. It's constant. So if we multiply both sides, let me do that. Calcium, let's see, 0.204. If we multiply both sides by that, break it off here, then we have calcium oxalate and the Kc, both of which are constants, and together they will equal the KSP. So very similar to what we saw with the Ka and the K, where we didn't include water, or the Kb, where we didn't include water. Now we're not including the solid. So the only thing that show up in the KSP expression are the ions, the products, but raised to their coefficient. So in this case, they're both 1 to 1, so everything's to the first power. Just interesting. Kidney stones are usually calcium phosphate or calcium oxalate. If you have too much of them, they can't stay dissolved anymore and they will precipitate out. So that's kind of what we're talking about in this chapter. So again, the KSP is equal to it's called the solubility product constant. That's where the SP, solubility product, and constant is K. So again, remember that we have to include coefficients. It's probably one of the things that's hardest, switching back to general equilibrium from acid-base equilibrium, because we get kind of lazy and forget our coefficients and raising power. So be careful about that. So lead iodide, when it dissolves, will break apart into 1 lead ion and 2 iodide ions. So you've had lots of practice with this back in the first chapter. So hopefully, if you're having a hard time breaking apart the ions, go back and look at chapter 4 and do a little bit of a review. But remember, like if I put 1 mole of lead iodide into solution, I'll get 1 mole of the lead ion, and I'll have 2 moles of the iodide ion. So again, be careful with the concentrations, and then also don't forget to raise the coefficient, raise to the power of the coefficient. So so for that previous one, here's the KSP expression. So lead iodide concentration, molar concentration, times the iodide concentration squared. Like all equilibrium constants, the KSP has fixed values at a given temperature. It may change depending on the temperature, but since we'll just be working at one temperature, the value will be fixed. And the KSP is the same regardless of the direction, and so it's the point where either everything dissolves or the point where precipitate starts. So we can use it when we're talking precipitate problems as well. So just to be clear, the names sound very similar to each other. Make sure you don't get them confused. The solubility product constant, again, I know we can't spell, so it's KSP. K constant SP. I guess it's better than, it's more usable than a C. Anyway, the solubility product constant is the KSP. The solubility just means how much can dissolve. What is the solubility of that? How much of it will dissolve? So solubility just is the quantity that dissolves to form a saturated solution. What is the maximum amount that can dissolve? When we're talking about those totally soluble ions, we don't have a solubility because it can keep going and going. But actually, even those sometimes, like sodium chloride, like you couldn't pour a whole bottle or whole canister of sodium chloride in a cup of water. So it does have its solubility as well. It has its maximum that will dissolve. And usually the solubility is expressed either as grams per liter, especially in other fields like geology, they'll often use grams per liter, or in chemistry we tend to use moles per liter or molar solubility. So you can convert back and forth between the two. And then of course the solubility product constant is just the equilibrium constant for the equilibrium expression. And if we, just like we did with Ka and Kb, like if we knew the pH, because that tells us H+, then we could find the Ka. If we knew the Ka, we could find the pH. It's going to be the same thing. If we know the solubility, we can find the solubility constant. If we know the solubility product constant, then we can find the solubility. So that's what we're going to do in a minute. All right, so let's look at that. So in 1 liter sample of saturated calcium oxalate, so the key is saturated, it's totally dissolved as much as it can, and that amount has dissolved, 0.0061 grams of the salt has dissolved and it's totally saturated. So that's the maximum that can dissolve. Find the KSP for this at 25 degrees. Since that's 25, don't worry about the temperature because they're just being clear that the KSP will change at different temperatures, but we're only worried about this particular temperature. So again, just remember our KSP is going to equal the calcium ion concentration times the oxalate ion concentration. Right now, this is and of course, if this wasn't 1 liter, you would want to, divide by the liters to get so this is 0.0061 grams per 1 liter is the solubility. Well, again, don't forget these brackets mean molar concentration, so we're going to have to convert grams per liter to moles per liter. So we just use the molecular weight, so 0.0061 grams per liter times 1 mole per 128 grams, so the grams will cancel and we'll end up with moles per liter. So 4.8 times 10 to the minus 5th, 10 to the minus 5th moles dissolve per liter. Now you don't have to set up an I believe we can. So that sometimes we don't put anything on this left-hand side when we're talking solubility. Sometimes I'll just put it here. I'm saying what's happening. Well, 4.8 times 10 to the minus 5th moles is dissolving. So that's how much of the solid is dissolving. Now, because the solid, there's so much solid that it's constant, we really don't use the equilibrium expression. It's not needed, so we don't have to worry about it. But just so you see the coefficient, 1 calcium oxalate will dissolve into 1 calcium, so 4.8 times 10 to the minus 5th molar will be 4.8 times 10 to the minus 5th molar calcium, and 4.8 times 10 to the minus 5th oxalate. So that's what our equilibrium expressions are. So we can plug the equation and solve for KSP, 2.3 times 10 to the minus 9. Just to clarify and make sure that you're following this, what if we had lead iodide? So that's the other one. Remember, lead iodide has 2 I's for every 1 lead, and so it's telling you that the solubility is 1.2 times 10 to the minus 3 moles per liter. Again, if it told you how much dissolved in 2 liters, you'd have to divide to find the per liter. So it's 1.2 times 10 to the minus 3 molar will dissolve. Don't forget, when we write this out, we have Pb2 plus 2I negative. The 2 I's will separate on their own, and we have 2 of them. So if we have 1.2 times 10 to the minus 3 moles of lead iodide that dissolves per liter, then we'll have 1.2 times 10 to the minus 3 moles of lead, but we'll have twice that, 2 times 1.2 times 10 to the minus 3 moles per liter of the iodide. So don't forget to multiply by 2. You can sort of see there. Again, you don't have to write this here, but what is this? Negative 1.2 times 10 to the minus 3 moles. And don't forget the coefficient. Now we can plug that into our equation, and also the other mistake I see often is people forget to square it. So double the concentration and square it. So the KSP for this is 6.9 times 10 to the minus 9th. More often, you're going to be doing the other one where you'll be given the KSP and try to find the solubility, which we'll do in a minute. So the table on the next slide will list the solubility product constants for various ionic compounds. Similar to Ka, the smaller the KSP, the less soluble it is. So the bigger the KSP, and since these are all to the negative exponents, remember it's the smaller the negative exponent, the larger the number is. So the 10 to the minus really big numbers will be very insoluble. And like I said, if we know the KSP, then we can find the solubility. We know how much can dissolve, and vice versa. So here are some KSP values. So if you're doing some homework and they don't give it to you, you can come and look it up. On a test, I would give you these values if it was required, if it wasn't where you had to find it, of course. But you can see some of the numbers, like iron hydroxide, very, very, very small KSP. So very little of that will, a lot of these leads have very small. Calcium oxalate, oh, that's cadmium oxalate, not so bad. But some of these are really tiny. Silver acetate will dissolve fairly well because 10 to the minus 3 is a much bigger number than some of these others. Anyway, tables of KSP values. All right, so now what if, so this is going to be similar to finding the pH if you know the Ka. Now we're going to, if we know the KSP, we're going to be able to find how much of the ions dissolve. What is the concentration of the ions that are dissolved? So again, it's all based on our equilibrium expression, either, you know, where we know, either we know the concentrations of the ions and we can find KSP, or we can find we know a KSP and we can find what the ions are. So very similar. So the mineral fluorite is calcium fluoride. Let's calculate the solubility in grams per liter of calcium fluoride in water if we know the KSP. So let's start by writing the equation. Calcium fluoride, when it dissolves, will form 1 calcium ion and 2 fluoride ions. We're going to let X be the molar solubility. In other words, how much of it will dissolve. So lots of times I'll put that there. How much of it will dissolve? That's X. X is how much will dissolve. So that means if X dissolves, we'll have X of calcium and 2X of fluoride. So X and 2X. Now we can plug that into our KSP expression, and of course we know KSP this time, so now we can solve for X. So calcium is X, fluoride is 2X. Because there's 2 of them, it's squared. So again, be really careful, take your time. So it's 2X quantity squared, and it equals the KSP value. So now we just have to solve for X, which is not too hard because 2X quantity squared is 4X squared times another X is 4X cubed. So this is 4X squared times X, so it's 4X cubed. Equals 3.4 times 10 to the minus 11th. So the first thing we have to do is divide by 4 and then take the cube root. And if you don't know how to find the cube root on your calculator, I might be able to help you or look it up. You'll have to be able to take a cube root or a 4th root or something like that. So it turns out that X is 2.0 times 10 to the minus 4th. And of course, since that's equal to, if we need units, of course that's equal to the calcium ion. But the fluoride ion then would be double that. But this is also equal to, that's why I like to put X on my chart, this is also equal to the calcium oxalate, or sorry, calcium fluoride, still on calcium oxide, calcium fluoride that can dissolve. So it's the molarity of calcium fluoride that can dissolve. And that's the solubility. Now, notice that it's asking for grams per liter. So because we know the moles per liter, we're just going to convert to grams per liter by multiplying by the molecular weight. So calcium fluoride, 78.1. So we could dissolve 1.6 times 10 to the minus 2, what is that, 0.016 grams of calcium fluoride per liter. So, like we've done in the last 2 chapters, either you can find KSP because you know what the ions are, or you can find the concentration of the ions if you know the KSP. Not too difficult.